Okay, Year 10. I'm going to take you through an example of a conservation of momentum question. This is the type of question that you're likely to get in the exam. These are some of the more complex calculation questions that you'll get, so you'll probably see them be worth 3 or 4 marks, and usually they'll come towards the end of the paper, unless they break them down step by step for you, in which case maybe you'll get, let's say, 3 1-mark questions earlier on in the paper. So, this is our question. We've got a car, it's moving. We've got a van, it's not moving. The car hits the van, and the van ends up moving. The concept that we're using to answer all of these questions is the conservation of momentum. The momentum before, on the left-hand side, is equal to the momentum after on the right-hand side. I'd like you to follow through these step-by-step methods every single time you do one of these questions. It's a lot easier to do it if you do it on paper than if you do it using, let's say, Word, but I'll have a go and try it with Word anyway. First step, draw 2 boxes. Label 1 before collision, 1 after collision. You can draw a little sketch if you want to show the objects, or you can just name them. Here I've chosen just to name them, call them car and van. We write what we know. Lay it out as you see here. Mass, velocity, and remember we use P for momentum. MVP for the car. MVP for the van. MVP for the car after the collision. MVP for the van after the collision. And all we want to do is we want to look at the questions very carefully and extract the information that we do know. So, scrolling back up to the question, what do we know? Well, the mass of the car is 1,200 kilograms. The mass of the van is 3,200 kilograms. In this case, we can make assumptions like their masses aren't going to change, they're not going to have bits fly off, even though we can see some debris on the road on the right-hand side, so that is technically a dodgy assumption. We do have to make that assumption. So the masses are the same. And before, the velocity of the car was 10 meters per second, and the velocity of the van was 0 meters per second. So we use those numbers and put them in here, here. Remember to tick if they have the correct units. If it's not the correct units, if they've given you grams or kilometers per hour, you have to convert until you have kilograms for mass and meters per second for velocity. That way, your momentum will always be in kilogram meters per second. So now, we calculate whatever we can. You will not be able to calculate everything in this second step. So, what can we calculate? Well, we know that the momentum of the car is 10 multiplied by 1,200. So that's 12,000 kilogram meters per second. What about the van before the collision? Well, it's not moving, so we don't have to think about it. If it's not moving, it doesn't have any momentum. And I'm going to say that the direction to the right-hand side that the car was going before is the direction that momentum is positive in. So if we had a situation where something ended up going backwards, then it would have negative momentum, minus some amount. What else can we calculate? Well, we can calculate the total momentum before. So how do you add momenta? Well, they're vectors. If they're in opposite directions, they cancel. If they're in the same directions, they just add. But here you've got 12,000 plus 0. So it's just 12,000 kilogram meters per second. Okay, can we calculate anything afterwards? Well, yeah, we can. Afterwards, the momentum of the car is 2 times 1,200. So that's 2,400 kilogram meters per second. Simple as that. That's step 2. Step 3 is just to use the idea that in a closed system, momentum has to be conserved. What you have before must be equal to what you have afterwards. So all that means is that that total P, that bottom part, is going to be the same for both boxes. So I can just copy over from one to the other straight away. 1,200 kilogram meters per second. Now, we use the same concept that we did before, that the momenta of the two objects, the car and the van, have to add up to give 1200. So something plus 2400 is equal to 12,000. Another way of saying that is that this unknown is equal to 12,000 minus 2,400, which is 9,600. I'll do a quick sense check. If I add that and that together, do they make 12,000? Well, 9,600 plus 400 is 10,000, plus 2,000 is 12,000. So they do. That was step 3. Now finally, step 4. You use everything that you have done so far to calculate the one thing that we don't yet know. The purpose of this question. What was the velocity of the van after the collision? How do we do that? Well, we need to rearrange the equation. We know that momentum is mass times velocity. We need to make velocity the subject of the equation. Now, some people find this more difficult. You can just remember the different forms of the equation if you want to. I find it easier to rearrange it each time, but it is up to you. So momentum is mass times velocity. So velocity is momentum divided by mass. Okay, have a look at the units. We want to get out meters per second. We've got kilogram meters per second, so if we divide by kilograms, the kilograms will cancel out. Kilogram divided by kilogram is just nothing. So, what do we have here? We've got 9,600 divided by 3,200. Put into a calculator if we need to. This is actually a nice number. We'll get out at 3 meters per second. And that is in the forward direction. It's a positive number, so it is going to be going to the right-hand side. Remember, it's asked for a velocity, so we should probably say 3 meters per second to the right. And that also makes sense, because if we look at the diagram, the car is moving at 2 meters per second to the right, so if the van was moving slower, then the car would be like phasing through it or something. It wouldn't be possible. So the van has to be moving faster than the car, assuming that they are all in a line, and this is a nice, relatively straightforward problem. There are some complications possible. So sometimes, actually, you don't end up with two objects. You just had two things, but they stick together. So afterwards, you can just consider that to be one object, and it makes your life much easier for calculations. It allows you to do some calculations you wouldn't do otherwise. Sometimes, things might end up going backwards, rebounding. And if they do, then you have to remember that because momentum is a vector, if it's going in the opposite direction to whatever you said was positive, it's negative. So treat that as a negative number if it's in the other direction. And then sometimes the most complex questions I've ever seen on this, they don't actually have the information that you start with. They give you all the information at the end, so you can fill out the whole of that after box. You have to work back in time to work out something that happened before. So you work from right to left instead of left to right. These are the questions I'd like you to try. They do get more difficult as we go on, but they start out relatively straightforward. I'd like you, please, to try to use this format. So I want to see two boxes. I want to see a before and after. I want to see a notation of either what the objects are, or maybe it's a sketch or something like that, and then MVP, MVP, MVP for all of the different objects. At the bottom, total P. All right, I want to see something that looks like that for every single one of your answers, even if you find these relatively straightforward. If you've got any questions, I'm obviously available via Teams. Let me know if you're having difficulty, and I'll give you a hand. Thank you very much, Year 10.